The values for inductive reactance, alternating current resistance, and effective impedance for conductor sizes omitted from Table 9, Chapter 9 are provided. These values are important for electrical calculations, specifically when dealing with larger conductors. For a 700 mcm conductor, the inductive reactance is 0.62 milliohms per meter, the alternating current resistance is 0.119 milliohms per meter, and the effective impedance is 0.136 milliohms per meter. For an 800 mcm conductor, the inductive reactance is 0.57 milliohms per meter, the alternating current resistance is 0.130 milliohms per meter, and the effective impedance is 0.146 milliohms per meter. For a 900 mcm conductor, the inductive reactance is 0.53 milliohms per meter, the alternating current resistance is 0.140 milliohms per meter, and the effective impedance is 0.153 milliohms per meter. For a 1250 mcm conductor, the inductive reactance is 0.45 milliohms per meter, the alternating current resistance is 0.171 milliohms per meter, and the effective impedance is 0.182 milliohms per meter. For a 1500 mcm conductor, the inductive reactance is 0.40 milliohms per meter, the alternating current resistance is 0.197 milliohms per meter, and the effective impedance is 0.206 milliohms per meter. For a 1750 mcm conductor, the inductive reactance is 0.38 milliohms per meter, the alternating current resistance is 0.216 milliohms per meter, and the effective impedance is 0.224 milliohms per meter. For a 2000 mcm conductor, the inductive reactance is 0.35 milliohms per meter, the alternating current resistance is 0.235 milliohms per meter, and the effective impedance is 0.241 milliohms per meter. The values provided were obtained from the IEEE Standard 241-2001, reaffirmed in 2020, and Bussmann Bulletin EPR-1. It's important to note that these values are approximate and can fluctuate based on the specific conductor material and its construction. For precise values, consult the relevant standards or a qualified electrician. Inductive reactance, often denoted as X sub L, is the opposition that a circuit presents to a change in current due to inductance. It is measured in ohms and is frequency dependent. The higher the frequency or inductance, the greater the inductive reactance. Alternating current resistance, also known as alternating current effective resistance, is the total opposition to current flow in an alternating current circuit, encompassing the direct current resistance and the increase in resistance due to skin effect and proximity effect. It's also measured in ohms. Effective impedance, represented as is the total opposition a circuit presents to alternating current. It's a combination of resistance and reactance, both inductive and capacitive. Impedance is also measured in ohms. Understanding these parameters is crucial for several reasons in electrical engineering. Firstly, voltage drop calculations. Knowing the impedance of conductors allows engineers to accurately calculate voltage drop in a circuit. Excessive voltage drop can lead to equipment malfunction and inefficiency. Secondly, short circuit current calculations. These parameters are essential for determining the magnitude of short circuit currents. This information is vital for selecting appropriate protective devices like circuit breakers and fuses to prevent equipment damage and ensure safety. Thirdly, power loss calculations. Alternating current resistance directly impacts power loss in conductors. Accurate resistance values are needed to estimate losses and optimize system efficiency. Fourthly, system design and analysis. These values are crucial for modeling and simulating electrical systems to ensure proper operation and stability. The skin effect is the tendency of alternating current to flow mostly near the outer surface of a conductor. This reduces the effective cross-sectional area of the conductor, increasing its alternating current resistance compared to its direct current resistance. The proximity effect is the distortion of current distribution in a conductor due to the presence of nearby conductors carrying alternating current. This effect also increases the alternating current resistance. The values presented are essential for electrical engineers, electricians, and anyone involved in the design, installation, and maintenance of electrical systems, especially those dealing with large conductors in industrial or commercial settings. When working with electrical systems, always prioritize safety. Ensure that you are qualified and familiar with relevant codes and standards. Always energize circuits before working on them and use appropriate personal protective equipment. It is advisable to consult with a qualified electrician or engineer for specific applications or complex calculations. They can provide expert guidance and ensure that the electrical system meets safety and performance requirements. Understanding the source of these values is also very important. IEEE Standard 241, often referred to as the IEEE Recommended Practice for Electric Power Systems in Commercial Buildings, provides comprehensive guidance on the design and operation of electrical power systems in commercial buildings. It includes detailed information on conductor characteristics, grounding, protection, and other essential aspects of electrical system design. Bussmann Bulletin EPR-1 focuses on surge protection devices. While it might not directly provide conductor characteristics, it often includes information relevant to system impedance and the impact of surges on electrical systems. Surge protection is crucial for protecting sensitive electronic equipment from voltage spikes and transients. These surges can be caused by lightning switching operations or other disturbances in the electrical grid. Surge protection devices, or SPDs, are designed to divert surge current away from protected equipment, preventing damage and ensuring reliable operation. When selecting conductors for a specific application, several factors must be considered. Firstly, current carrying capacity or ampacity. The conductor must be able to safely carry the anticipated current without overheating. Ampacity is determined by conductor size, insulation type, and ambient temperature. Secondly, voltage drop. The conductor must be sized to limit voltage drop to acceptable levels. Excessive voltage drop can impair the performance of connected equipment. Thirdly, insulation type. The insulation must be appropriate for the application and environmental conditions. Factors to consider include temperature rating, moisture resistance, and chemical resistance. Fourthly, environmental conditions. The installation environment can significantly impact conductor performance and longevity. Factors such as temperature, humidity, and exposure to chemicals or sunlight must be taken into account. Fifthly, mechanical strength. The conductor must have adequate mechanical strength to withstand the stresses of installation and operation. This is particularly important for overhead conductors or those subject to physical abuse. When using tables like Table 9 in Chapter 9 of the National Electrical Code, or NEC, it's important to understand their limitations. These tables typically provide values for common conductor sizes and types under specific conditions. However, they may not cover all possible scenarios or conductor configurations. Always refer to the NEC for the most up-to-date requirements and consult with a qualified electrician or engineer for situations not explicitly covered in the code. The alternating current resistance is typically higher than the direct current resistance due to the skin effect and proximity effect. The skin effect causes current to concentrate near the surface of the conductor, reducing the effective cross-sectional area and increasing resistance. The proximity effect is the distortion of current distribution in a conductor due to the presence of nearby conductors carrying alternating current. This effect also increases the alternating current resistance. The inductive reactance of a conductor is determined by its geometry and the frequency of the alternating current. Inductive reactance increases with frequency and inductance. Inductance is a property of a conductor that opposes changes in current flow. The effective impedance of a conductor is the vector sum of its alternating current resistance and inductive reactance. Impedance is a measure of the total opposition to current flow in an alternating current circuit. It's important to use the correct impedance value when calculating voltage drop, short circuit current, and other circuit parameters. In summary, understanding the values for inductive reactance, alternating current resistance, and effective impedance for various conductor sizes is crucial for accurate electrical calculations and safe electrical system design. Always refer to relevant standards and consult with qualified professionals for specific applications and complex situations. Accurate conductor parameter values are crucial for performing power system studies, including load flow analysis, short circuit analysis, and transient stability analysis. Load flow analysis determines the voltage and current distribution throughout the power system under normal operating conditions. Short circuit analysis calculates the magnitude of fault currents during abnormal conditions, such as short circuits. Transient stability analysis assesses the ability of the power system to maintain stability following a disturbance, such as a sudden load change or a fault. Using accurate conductor parameters in these studies ensures that the results are reliable and can be used to make informed decisions about system design and operation. For example, accurate short-circuit current calculations are essential for selecting appropriate protective devices, such as circuit breakers and fuses, to protect equipment from damage during fault conditions. Similarly, accurate load flow analysis is necessary for determining the optimal placement of capacitors to improve voltage regulation and reduce power losses. The values for inductive reactance, alternating current resistance, and effective impedance can also be used to assess the impact of harmonics on power system performance. Harmonics are sinusoidal voltages and currents with frequencies that are integer multiples of the fundamental frequency. Harmonics can cause a variety of problems, including increased power losses, equipment overheating, and distorted voltage waveforms. By knowing the conductor parameters, it is possible to calculate the harmonic impedance of the power system and determine the magnitude of harmonic currents and voltages. This information can be used to design filters to mitigate the effects of harmonics. Furthermore, understanding these parameters is essential for proper grounding and bonding practices. Grounding and bonding are critical for ensuring electrical safety and preventing electric shock hazards. Proper grounding and bonding practices provide a low impedance path for fault currents to flow back to the source, allowing protective devices to quickly clear the fault and prevent dangerous voltages from developing on equipment enclosures. The values for inductive reactance, alternating current resistance, and effective impedance are used to calculate the impedance of grounding conductors and bonding jumpers, ensuring that they are sized appropriately to safely carry fault currents. Additionally, knowledge of conductor parameters is valuable for troubleshooting electrical problems. When diagnosing voltage drop issues, excessive heating of conductors, or unexplained equipment malfunctions, accurate conductor parameter values can help pinpoint the source of the problem and identify the appropriate corrective actions. For instance, if a conductor is found to be overheating, the alternating current resistance can be measured to determine if it is higher than expected. A higher than expected resistance could indicate a loose connection, corrosion, or damage to the conductor. In addition to the IEEE and Bussmann resources, there are other sources of information on conductor parameters. Firstly, conductor manufacturers. Conductor manufacturers typically provide detailed specifications for their products, including values for inductive reactance, alternating current resistance, and effective impedance. Secondly, industry standards organizations. Organizations such as the National Electrical Manufacturers Association, or NEMA, and the Insulated Cable Engineers Association, or ICE, publish standards that include information on conductor characteristics. Thirdly, engineering textbooks and handbooks. Many engineering textbooks and handbooks contain tables and formulas for calculating conductor parameters. In conclusion, having access to accurate values for inductive reactance, alternating current resistance, and effective impedance for various conductor sizes is essential for a wide range of electrical engineering applications. These values are used for power system studies, harmonic analysis, grounding and bonding design, troubleshooting, and ensuring the safe and reliable operation of electrical systems.